Okay. So last class we left off talking about the binomial. We'll finish up our discussion on it today. I might introduce the Poisson at the very end of class, but something I wanted to mention before we get going is a little bit about the exam. So what we'll do for the exam, so next Monday, right, our in-class meeting time, I'll basically be doing problems from the practice exams, okay? So if I will open the exam up early Monday morning, like 7. I don't think any of you probably want to take it before 7, but it'll be open early. You'll have, if you want to, any time during the day Monday to take it. I would suggest waiting until after we do some more of that review. But depending on your schedule, if you want to, you can take it prior to that extra review session. You can also take it at any point on Tuesday, right? So it'll kind of be open for about a little less than 48 hours, since I'll kind of post it or have it be available Monday morning until the end of the day on Tuesday. Once you start it, you'll have, I'm not sure exactly yet. It's going to be somewhere between an hour to an hour and a half, probably split the middle. It's probably about an hour and 15. I'm still kind of finished putting in certain questions and figuring out exactly what I want the composition to look like. So somewhere between an hour and a half once you start it to complete it and submit it. It'll look really similar to the practice exams in that the majority questions, and it'll be about 20 questions, will be multiple choice. But the last question will be kind of a short answer with some potential parts to it. So part A, B, or C. For that short answer, you can do your work in Excel. You can type out what your work is in Word, or you can take pictures of your work and upload those pictures as part of your answer to the short answer as well. Now, I don't know if I've had some questions. I don't know if any of you have had other professors use kind of that short answer where you can upload files, but it's pretty easy. Like once you get to that question, it has a pretty obvious button you can click on where you can upload files, and you can upload photos from your phone. You can upload Excel files, Word files, pretty much any file that you would want, right? So however you do your work, you can upload it in that form, okay? Yeah.
I don't know if you answered this already, but will you be taking this through the lockdown browser?
So the tentative answer is no. I was playing around with it, because what I want you to be able to do is, if you want to use Excel, I want you to be able to do that. The problem is I played around with putting Excel into Respondus, and it is hard to use. And also, I couldn't get the binomial function to work correctly. It was giving me things that were not between 0 and 1. So I think that it's kind of limited in how it allows you to use Excel in that. So I likely won't be, which means that I'm kind of expecting you guys to follow some academic integrity. Honestly, you can Google all you want. You're not going to find my exact problems out there. So the numbers are going to be different. Some of the stuff will be a little bit different. And so I'm not super worried about you kind of using the web browser in terms of searching for things, because I want you to be able to have that formula sheet open. I want you to be able, if you want to, use Excel. I just kind of count on you not to be working with other people or kind of things like that. Although there's other things I'll do with the exam that'll prevent that too. So some of you might see slightly different questions than others and slightly different numbers. And so I'm not overly concerned. If I could have used that, I would. But like I said, it just doesn't give us the option to really use Excel in what I think is in the way that I would want you to be able to use it if you do want to use that on the exam. Yep. Yep. That was answering the question. Hopefully I should repeat it. That whether or not we'll be using Respondus. So we won't be 99% sure that we won't be, unless I can get Excel to work better in it. Okay. Any questions for me? Anything else on the exam other than that? We'll jump into things. Okay. So I believe where we left off last class was we went through the first example for these binomial distribution examples. We used a coin flip example. I think I even introduced the next example where we're looking at, well, if there's a 30% chance that someone has a college degree, what's the probability that we see 3 out of 5 have a degree? But I want to move some of the slides around. I want to change the discussion of what I originally wanted to start out with. So I'm going to start here. And this should be pretty kind of simple. So if I flip a coin 100 times, and the probability that I get a heads is 0.5, out of 100 coin flips, on average, how many would I expect come up heads. If I flip a coin 100 times, on average, the most common number I'll get is 50, right? And so you did that kind of intuitively, but really what you did in your head was you took the number of trials, 100, and you multiplied it by the probability of success on any one trial, right? So that's how we can get the mean or the expected value, right? Because this is still a discrete random variable, right? So this is the mean or the expected value of our binomial is simply this equation of n times p, your number of trials times your probability of success. And like I said, for a lot of people, that'll just be intuitive, something you can do in your head pretty quick, if the numbers are easy. The variance, we could Google, we could walk through the mathematical proof if we wanted to. It's not really interesting, but no matter what your number of trials, what your probability of success is, your variance will always be n times p times 1 minus p, right? So it just follows this really simple formula every single time, right? And if I want the standard deviation, just like always, all I have to do is take the square root, okay? Make sure. Okay, I was gonna say, second guess myself, like leaving the oven on that didn't hit record sometimes. So all we do is take the square root there, right? Just like we always do. So if I had this example that we had just left off on last class where 30% of adults have a college degree. So if I chose any one person at random, the probability they have a degree is 0.3. I'm looking at 5 randomly selected adults. So my number of trials is 5. And I might be interested in what's the mean and the variance, right? Well, the mean is simply take that number of trials, 5, multiply by that probability of success in any one trial, 0.3. That should give me 1.5. So I've got that mean, that expected number of successes. How do I find the variance? Well, that was just n times p, so 5 times 0.3, times 1 minus p, so times what, 0.7? And that should give me 1.05, right? I mean, if I ask you a question on the exam I give you some setup that it's clear that it's a binomial distribution example, to find the mean and the variance of it, I mean, these should be pretty easy, right? And if I wanted the standard deviation, all I do is take the square root there, just one more step, right? So for this example, the mean or expected number of people that have a college degree out of 5 is 1.5. Well, now when we actually look at the 5 people, we can't see 1.5 person have a college degree. Either 0 people have a degree, 1 person has a degree, exactly 2, exactly 3. So if 1.5 is the mean or the expected value, what we know is, well, 1 and 2 will then be the most likely outcomes that we'll see. If the expected value is not an integer, if the expected value is 1.5, then the values we would expect to see most often or have the highest probability of occurring would be the values that are on either side of that, right? So 1 and 2. Now, if I have an integer, like in my coin flip example, if I flip a coin 100 times, the expected value of number of heads is 50, then the most likely outcome will be 50. Right? That one's a little bit easier. But if I'm in between here, the most likely outcomes will be the values on either side. And now, as I move further from that mean, right, the values, the probabilities of seeing that number of successes starts to fall. And this is somewhat intuitive, right? If 30% of people have a college degree, and let's say instead of 5, to make it easier, we say that we were looking at 10 people. Well, on average, we would expect 3 people to have a degree, right? And we would know that the probability that all 10 have a degree is pretty low, right? Why is it pretty low intuitively? Because you're very far away from what that expected value is. So as we move away in either direction from that expected value, we should start to see the probabilities decline, right? So if I go to this example, right, and I say, what's the probability that exactly 3 people have a college degree? Well, I'm looking for the probability that x is equal to 3. So my x is 3, my number of trials is 5, and my probability of success is 0.3. Right? So I've got the 3 things I need. Where is it? To plug into this equation to find the probability that x is 3, or I see 3 successes. Right? So I'll go ahead. Oops. I get my 3 pieces of information I need. I plug in 5 where I see n, 0.3 where I see p, 3 where I see x, right? Once again, I think I mentioned this last class, but the way I would do this still looks like kind of a nasty formula. Simplify everything you can in your head. Rewrite, instead of putting 5 minus 3 and writing that in parentheses, write down the number 2, right? Like, just make it easier for yourself. Don't have to deal with this many parentheses. 1 minus 0.3, write down 0.7, 5 minus 3, write down 2 there, right? Do the math you can do in your head before you write out this entire equation, just to make it easier once you go to your calculator, you know, you're not messing around with a bunch of parentheses, okay? So if we, you know, at this point, you know, once we get the information that we need and we have identified it, we plug it into this equation. At this point, it's really just you getting more practice, you trying to recreate these numbers that in the examples that we worked through in class, or, you know, practicing the binomial equations on those practice exams to make sure that you can, once you get this in the right, you know, you have the right numbers plugged in correctly, now it's just a matter of using your calculator correctly, right? That's all it is at that point. So just getting more comfortable with that, working through more examples on your own, feeling comfortable, finding that factorial button on your calculator and computing this. Okay? So if the probability that I see 3 out of these 5 have a college degree is 0.13, let's say I change that, and now I want to find the probability that exactly 4 people have a degree. If I found the probability that 3 have a degree is 0.13, which of these do I know has to be the correct answer? Remember, what was the expected number of people? 1.5. So if I found that the probability that 3 have a degree is 0.13, which of these has to be the probability that 4 have a degree? D? So if I think about this, if I go from 3 to 4, I'm moving further away from the expected value of 1.5. So that probability of seeing 4 should actually be lower than it was for 3. So the probability that it was 3 is 0.13. The probability that it's 4 has to be lower than that. The only one here that's lower than that is 0.028. Right? Yeah, so you don't want to, we're not thinking about complements yet, right? We'll see in a second here, we can do some stuff with complements where we're subtracting things from 1. But here I'm just generally talking about as we move further from that expected value, the probability of those outcomes starts to decline. I'll show you some other pictures here in just a second that kind of reconfirm that. Okay? So if I wanted to say find the probability that 5 people have a degree, what do you think that's probably going to be pretty close to? If going from 3 people to 4 people drop the probability from 0.1 to 0.028, if I look at the probability that 5 people have a degree, what's that going to be pretty close to? 0, right? Yeah. So I don't have it right here, but yeah, as we move further, it's just going to get closer and closer to 0. Good. So we can, you know, plug that in and actually reproduce that answer. Now, one thing I'll point out here, this simplifies a lot. So, you know, 0.3 to the 4th power times 0.7 to the 1 power, right? So just 0.7. I can find this in my calculator pretty easily. If I wanted to rewrite this, still kind of looks like a mess. Just kind of a reminder of some of the stuff we can do here. Let's get rid of this. 5 factorial over 4 factorial times 5 minus 4. All right. First of all, this is just 1 factorial. 1 factorial is just 1. So I can kind of ignore that. Multiplying or dividing anything by 1 is the same thing. If I were to write these out, 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1 times, I guess, technically 1 if we wanted to. Well, notice everything here cancels. I've got 5 divided by 1, which is just 5, right? And if you can't see anything here, let me know since we got this in the way. Okay. Also, if you're in person, look at what I'm doing here. This is obviously backwards. So I saw you looking at the screen. Look right here, and if you can't see it, because you're in the back or something, ask me, okay? Any questions on that? So we can kind of simplify things a lot if we write some of these factorials out sometimes, especially with these smaller values. Okay, so now what if I want the probability, same numbers, but now I want, what's the probability at least 3 out of the 5 have a college degree, all right? So I want the probability that at least 3 out of 5, okay? So what I'm going to do there is, the first thing I'm going to do is write out in terms of the probability what that looks like. So I've got the probability of being at least 3 would be greater than or equal to 3. Right? So the way in which we would find something like this is we think about every single outcome that would fit this criteria. And because we're thinking about, well, I can only see exactly 3 people have a college degree or exactly 4, right? We can think about them as mutually exclusive events. When we're looking at the union of mutually exclusive events, that means the intersection is 0. So we simply just add the probabilities of the events together, right? That's kind of going on behind the scenes. But the way I would describe this is think about what fits this category or this criteria, and then find the probability of every number of outcomes that fits this criteria and add them all up. So here, if I want that probably x is greater than or equal to 3, I could see 3 people have a college degree. That fits this criteria. I could see 4 people have a degree. Excuse me, I could see exactly 5 people, but then I have to stop, right? That's my number of trials. I can't have 6 out of 5, right? So really I could rewrite this as the probability that x is equal to 3 plus the probability x is equal to 4 plus the probability x is equal to 5, right? Now, to find each one of these probabilities, I'm going to have to use that binomial equation each time. So I'll use it here and plug in for x3. I'll use it here, but now x will be 4, and then I'll use it again here, but x will be 5, right? And so once I use that 3 times and then add them up, that gives me the probability x is greater than or equal to 3, right? So we go here. I think I have this on this, actually written on the slide, right? And ignore this line for just 1 second. But I could rewrite this as the probability x is equal to 3, 4, and 5. Now, I use these values because we already found the probability that it was equal to 3 and equal to 4, right? So really the only thing left we have to do is find the probability x is equal to 5. So here's kind of the equation we use to find the probability x is equal to 3, 0.132, 4, 0.028. Now I find that last piece of information I didn't have, which is that the probability x is equal to 5. Now my n and my x are 5, right? So we said it would be pretty close to 0. Sure enough, 0.002. But also, if I write this out, anytime I'm looking for are all of the trial successes, right? Are 5 out of the 5 successes, or the 5 out of the 5 people have a college degree. If I write this out and just plug the numbers in, look at how much cancels. 5 minus 5 is 0. Anything to the 0 power is 1, right? So that I can almost ignore that. Can't ignore this, 0.3 to the 5th. 5 factorial divided by 5 factorial times 0 factorial, which we said 0 factorial is 1. So this is just 5 factorial over 5 factorial. This all cancels. So if you're actually looking for like the maximum number, like out of n trials, all of them are a success. This was 1, this was 1. It's really just taking that probability of success and raising it to whatever power the number of trials is. Okay. Is there anything else I want to say here? So we'll add all these up. We'll get 0.162, and that would be the probability that we see x be 3 or higher. Does that make sense? So kind of the way I describe it, I mean, we could, like I said, behind the scenes, there's really this idea that you're looking for the union, and because they're mutually exclusive, the intersection is 0, and you can just add the probabilities up. I always just say, like, write out what you're looking for. You want x is greater than or equal to 3. Think about every outcome that fits that criteria. So 3, 4, and 5. Find the probability of each one of those outcomes, and then add them up. Right? Any questions on that before we keep moving? So what did I do kind of right here? So I'm going to show you another way we could find this, right? Since we already had these pieces of information, it was pretty easy to do it this way. But I'll show you this example and a more extreme example of why we might want to do it in a different way. Okay, so if I want the probability that x is greater than or equal to 3, I can think about this as event A. So if I want to find the probability of A, if I use my complement rule, I know that's the same as 1 minus the probability of its complement. Remember, complement just means everything that's not in A. So if A is x being greater than or equal to 3, a complement would just be x is I'm thinking about the complement is anything not in A. So all the X values in A are 3 or higher. So an A complement would be all the values less than 3, right? Okay, so I'm just like writing the opposite of whatever A is, right? Complements, essentially, you can think about it as like kind of the opposite. Well, now, how could I rewrite this? Well, all the outcomes that are less than 3, well, the first outcome that's less than 3 would be 2 people. So the probability X is equal to 2, plus the probability X is equal to 1. And then don't forget, right, the probability that X is equal to 0 as well. All right, so probability X is equal to 2, plus the probability X is equal to 1, plus the probability X is equal to 0. Right? Once we add those up, we would have this, which is the probability of A complement, and subtract it from 1. Okay? That's another way that we could find it. Right? Now, we didn't have these, so we would have to use the binomial equation 3 times. So that's why I showed you the first way, because we already had a lot of the information. Right? And this wouldn't really save us any time because we still have to use that binomial equation 3 times, which is what we did right here as well. So either way doesn't really save me any time. I have to use that binomial equation 3 times. But in some situations, using this complement rule is really important, right? So I'll show you another example where using that complement rule is really important, right? So let's say, I don't know, doesn't matter what example, let's do a coin flip one. And I'm flipping the coin 100 times, right? And maybe I want the probability that I see at least 2 of those 100, right, be heads. So I want probably that X is greater than or equal to 2. Well, if I broke down the way I originally said this, I take everything that fits this criteria and I add up the probability of every one of those possible outcomes. But what fits this criteria? The probability X is equal to 2, plus the probability X is equal to 3, plus the probability X is equal to 4, all the way up to 100. I'm going to be here all day with that binomial equation trying to do that, right? So anytime you have an example and you think about what fits the criteria, you're like, man, there's like, even if I'm using the equation 4 or 5 times, there's probably an easier way to do this. Professor Landis wouldn't give me one where I had to take this much time to solve this problem. Well, if we think about this as event A, how can I rewrite this using that complement rule? Just 1 minus the complement. So what's the complement here? If A is that X is greater than or equal to 2, X complement would be what? Yeah. Just the opposite of that, right? Now you have to be careful of your equalities, right? You don't want to put less than or equal to because now the equal is in both. The idea of a complement is that it's everything that's not in A, so you can't have something that's in both of them. So if you've got the equality up here in event A, you need to make sure you don't put it here. Right? Now, what's everything that fits this criteria? Well, X could be 0. X could be 1, but it can't be 2, right? Because we're still dealing with a discrete random variable. Okay? So here, now I only have to use that binomial equation 2 times instead of what, like 98 times up here, right? So it saves me a lot of time. I mean, it actually just makes it more of a practical question I can actually answer, okay? So anytime, like I said, on the exam or even in homework, if you're looking at something and you think about what fits the criteria of the event you're interested in finding the probability of, if you're using that binomial equation more than 4 or 5 times, there's no way I'm expecting you to solve it that way. You can probably use this complement rule and save yourself a lot of time, okay? Excuse me. Any questions on this? We're okay with this? We're sure? Okay. All right. This will become important for part of Friday's discussion as well. All right. So we already went through this. So here's the other one. I said I had some more pictures because I really want to hammer home this idea because it can prevent you from making some pretty easy mistakes just to not get lost in the formula and remember some traits about these distributions. So I'll start with this middle picture here, right? So I'm going to deal with all these are binomial examples. This one I have n is 5 and the probability of success is 0.5. So what's my expected value or my mean? Well, that was where we just did n times p, so 5 times 0.5. The expected value would be 2.5. Well, I can't see 2.5, it's a discrete variable. So what that tells me is if the mean is 2.5, the most likely outcomes would be 2 and 3. Sure enough, I look here, and these are the actual values. 2 and 3 are the most likely outcomes. And then as I move in either direction away from that mean, the probabilities decline, right? So if I instead use that same probability of success, but I go to n is equal to 50, notice my expected value here, 50 times 0.5 is 25, so that's the most likely outcome. And then as I move in either direction, it starts to fall, and the probability of those outcomes start to fall. And notice here, if I'm flipping a coin essentially, right, probably with 0.5, 50 times, what's the probability all 50 are heads? Essentially 0, right? Really only the values that are near that mean have, probabilities that are kind of far away from 0, okay? Now, if I go back here now, smaller sample sizes, and I look at when the number of trials is 5, probability of success is 0.1, my expected value or my mean would be what? N is 5, probability of success is 0.1. My mean would be there, just n times p, so 0.5, right? 5 times 0.1. So the expected value is 0.5, which means the most likely outcomes will be 0 and 1, right? Sure enough, they don't have the same likelihood of occurring, but they are the two most likely outcomes here. And then as I move further away from that 0.5, that mean or expected value of 0.5, the probability of seeing a higher number of successes falls. Similar over here, the expected value, 5 times 0.9, 4.5, so 4 and 5 are the most likely outcomes. And as I move away from that mean or expected value, the probabilities of seeing those lower number of successes, right, further away from that mean or expected value start to decline. So sometimes people look at these and they get a little confused, especially at this top row. Whenever I'm like caught in the middle, right, like my expected value is not an integer, so it was 2.5, why is it then 2 and 3 had the same likelihood of occurring, but when the probability or when the expected value was 0.5, the probability of 0 and 1 weren't the same, right? Well, we're still dealing with a mean. This expected value is still a mean, and so it will be influenced by like outliers or extremely high values. Now here I use the term loosely, extremely, but notice when I'm dealing with that expected value of 0.5, the lowest possible value I could see is 0. So there's really only one value to the left of it, but there's like, a lot more values to the right. So this 4, 3, and 5, even though they have low probabilities of occurring, they're going to pull that mean up. So they're pulling that mean up to be 0.5, even though the most likely outcome we see is 0, right? So that's why if we don't have kind of a mean that's smack dab in the middle of the possible number of successes, we end up with, when the expected value is 0.5, 0 and 1 will be the most likely, but they won't have the same probability. Now, if that expected value is smack dab in the middle, like 2.5 here, well, there's equal number of possible outcomes to the left and the right, and so the mean doesn't get pulled in either one direction, and so that's why we ended up with 2 and 3 having equal likelihood occurring here. Okay? I'm not going to necessarily like quiz you or test you on that, but I want to give some intuition behind that because I know a lot of people that look at that and think, why is that happening? Here? Yep, right, think about it this way. 4.5 was the mean there. So 4 and 5 were the most likely. But, right, to get that expected value of 4.5, why was it pulled that much further away from 5, even though 5 was really likely to occur? Well, because we have extremely low values that were pulling that mean down to 4.5, even though 5 really was the most likely outcome that we could see. Yep, it's just same thing, but flipped. Any questions on that before we keep moving? And the question there that I was answering was, does it work the same for this one? So hopefully we're kind of able to follow that. All right, I'm going to skip these slides because I usually end up confusing people more than it helps. But the purpose of these slides is essentially that I gave you the mean and the variance equations for the binomial distribution. If you wanted to treat it like a normal generic discrete random variable and like take every single possible outcome, multiply by the probability that you see it, you could do it that way. And you'll get the same mean. So in this example, you get a mean of 2, as if you use that simplified binomial equation. Like I said, I'm not going to waste a lot of time on this because it usually ends up kind of confusing people. But I do want to make that connection that even if we treated this as a discrete random variable, just a general one and not as specifically as a binomial, we'd still find the same mean. It's just that because it is binomial, we have an easier equation to find that mean. Same thing for the variance. We could treat this as like a regular discrete random variable. We'd find a variance of 1.8. But if we use this simplified formula, it's a lot easier to get there, right? So I'm not going to worry too much about these. This is kind of something I wanted to mention. We'll walk through a few binomial examples just to kind of give you an idea about what you can apply this to. So which of the following would not be an appropriate situation where we could use a binomial? Okay. So remember, what we need for a binomial is that we have a success failure. The probability of success in any one trial is the same across all the trials. And we need to have some cap, right, where we could see like the total number of trials is 20. Right? So if I wanted to calculate the expected number of coin flips that come up heads in 123 coin flips, well, I've got my n there is 123. My success is that I see it come up heads. The probability of success is the same on every coin flip. And so I can apply the binomial here, right? The expected value of finding the mean, 123 times 0.5, right? Because I'm assuming I should have put in a fair coin here, but yeah. So that one works. Calculating the probability that at least 5 out of 20 patients will get sick or nauseous from an antibiotic. Let's assume that everyone has the same reactions to this antibiotic or kind of the same genetic like responses. Then the probability that any one person gets sick, there would be some underlying probability. I didn't give it to you here, but we would assume that probably any one person gets sick is the same across people. I have a number of trials here capped out at 20. My success, weirdly enough, is seeing someone get sick or nauseous from this antibiotic. And so I could very easily treat this as a binomial too. Okay. Calculating the probability that air traffic controllers at the Muncie airport make 3 errors per week. Well, I mean, okay. The success is that they make an error. Kind of weird, but the failure is that they didn't. The probability that I make an error on any given flight is probably the same, or any given landing is the same. But what am I capped out at here? Well, that's the thing, right? I'm thinking this, I'm like, okay, it's a week. So is it 7 days? Well, no, 7, I'm looking for the number of errors. So I can't be capped out at 7 days. So it's like, well, I don't really have an N here, right? If I was told every week there are 50 flights or something like that, then I'd be okay. But because it's just an open-ended interval, I actually don't have a cap amount, right? And a total number of trials N here. So I actually couldn't use it there, right? This will be like what looks like we introduced the idea of, which is the Poisson distribution here before we get out of class. And then the last one, if the probability that once someone enters a store that they make a purchase is the same across customers, or I just use kind of the average. If I look at 5 customers, what's the probability that exactly 3 make a purchase? Well, my success there is they make a purchase. The probability that once they enter the store, they make a purchase is the same. Be one I could pretty easily kind of use the binomial for as well. This might be something I'm interested in, right? If I know that I get 100 customers a day, and I know on average that, this one makes a little more sense if you think about like impulse items, that on average, the probability that somebody purchases an impulse item as they're checking out is 0.05. How many people would I expect to make one of those impulse purchases that day? Right? So that's another pretty good example, like pretty relevant or a pretty real application of using the binomial. Okay. Any questions on that before we kind of move on here? All right. I'm going to not go through these slides. They're going to be kind of for reference, but I want to show you a little bit of stuff in Excel. So the binomial equation, it's much easier to use in Excel than do by hand. So I'm going to just set this up initially. I'm going to put N for my number of trials, X for my number of successes, and P for my probability of success. In fact, it might be easier if I actually just order it this way. I'm going to go X and P. Right? If I then say, want to define, so I have this example that I put in the slides is, maybe we're looking at Detroit home foreclosures. So the probability, if you selected one house at random in Detroit, the probability it's foreclosed on, at least this was a couple years ago, was like 0.047 or 4.7%. Right? So let's say I look at 100 homes, and I want to know what's the probability that exactly 8 of them are foreclosed on. Right? Well, my success there is that the home is foreclosed on. The probability that any one house I'm choosing at random is foreclosed on is 0.047. And I'm looking for the number of successes to be 8. Right? So what I can do is use that equation in Excel that's called binom.dist. The first thing I select is the number of successes I'm interested in. Well, I said that was 8. I'll put it up in this cell here in just a second, but if I wanted to keep this general so I could use this for any example that had a binomial, this is the cell I'm going to put my number of successes I'm interested in. Comma, the second thing I need to tell it is the number of trials. That's my N. I'll put that right there. And the probability of success is P, which is going to be here. And then for now, this last thing, which is cumulative, right? This cumulative is like a yes, no. So if I put a 0, nope, I forgot my comma. If I put a 0, what that's telling Excel is, no, I don't want this to be cumulative. I want exactly the probability that it's equal to 8. If I put a 1 in there, what that tells Excel to do is, yeah, make it cumulative. Find the probability that it's equal to 8, add that to the probability it's equal to 7, add that to the probability it's equal to 6, and kind of go all the way down to 0, right? So that's not what I want to do here. I just want the probability it's exactly equal to 8, right? So I'll hit enter here. Now, obviously, I'm going to actually move this over to give myself some space. Or if you don't want to do that, you could have like inserted another row here. So here I said, what's the probability 8 homes are foreclosed on out of 100? And the probability any one home is foreclosed upon was 4.7% or 0.047. Right? So once I do that, I get the probability that out of 100, exactly 8 homes are foreclosed on is about 5%. What, 5.3% or 0.053. So this was the probability that X was exactly equal to 8. Okay? And now what's nice if I set this up like this and I'm working on a couple problems, what if I wanted to change this to 10? I just changed X to 10 and now I find the probability that X is equal to 10. Right? I'll turn it back to 8 because that's what we originally, I think that's what's in the slides. Okay? Any questions on that? So the order goes number of successes, comma, number of trials, comma, probability of success, comma, 0. If we want exactly the probability of 8 or whatever number of successes we're interested in. Now, what if I wanted the probability that X is less than or equal to 8? Right? Now, if we do this by hand, we know that what fits that criteria. Well, we'll take the probability it's equal to 8 plus the probability it's equal to 7 plus the probability it's equal to 6 all the way down to 0. Right? In Excel, instead of using, in 8 different cells, finding the probability it's equal to 8 plus 7 and adding all those up, we can actually use a feature of this binomial distribution that will do all that for us behind the scenes. So it asks, okay, what number do you want to start at and kind of work back to 0, right? Make it cumulative. So I'll say, well, I want the number of successes to be 8. The number of trials is 100. The probability of success is 0.047. But now I'll put a 1 in there as the fourth argument, which makes it cumulative, which says start at 8, find the probability it's equal to 8, and go all the way back to 0 and add up all those probabilities, right? So if I do that, get about 0.95, which kind of makes sense, right? I mean, the expected value here would be what? 100 times 0.047, so 4.7. So if I'm taking the probability of 8 and adding all the way back to 0, that's going to include all the most likely outcomes I could see. Right? But that putting a 1 in there is the last thing in that binomial.dist function, tells Excel, start at 8, find the probability of 8, add it to the probability of 7, add it to the probability it's equal to 6, and it does all that behind the scenes. Okay? Any questions on that before we keep moving? What if I wanted the probability that x is greater than 8? What could I very easily do here to find that? So there's no option in Excel to go forward, but if I know the probability x is less than or equal to 8, how could I find the probability x is greater than 8? Yeah, if this is A, well, this is just A complement. So 1 minus that. Right? So that's pretty easy. I'll show you one more that's a little tricky. Let's say I wanted the probability x is greater than or equal to 10. Okay? How could I find this? Well, right away, we should be thinking about, I'm going to have to use that complement rule. So equals 1 minus. And actually, before I do this, I'm going to write this out down here. So 1 minus the probability that x is less than 10, right? Just rewrite that as 1 minus the complement. So equals 1 minus the binom.dist. The number of successes here I want to put in. If I put 10 in, and then here's my number of trials, comma, here's my probability of success, comma, 1. Right? What this is actually going to return to me is the probability that x is equal to 10 plus the probability x is equal to 9 all the way down to 0, but I only want the probability x is less than 10. So instead of 10 here, what should I put? Yep, I'll actually put 9, right? Because that's the first number that fits this criteria. So this binom.dist, when you're using that equation, if I want something like the probability x is less than 10, what I actually have to put into the binomial equation is the first outcome that fits your event. And if x is less than 10, the first outcome that fits that criteria is 9. Okay? So the first one was a little different, right? Because there, I didn't want I wanted is it less than or equal to 8. So in that one, the very first outcome that fits this criteria is 8. But when I have just less than 10, the first outcome that fits that criteria isn't 10 because I just have, is it less than 10? The first outcome that fits that criteria would be 9. Yep. So that one is a little tricky when you don't have that equality and you're looking for the less than. Okay? Any other questions on that before we? That's all I want to show you. Oh, I'll show you one more thing that's kind of neat in Excel, but I'll do it real quick. Any other questions? So one thing, I could set up, like if I'm like the bank or I'm an insurance company, I'm thinking about foreclosures or claims, I probably want to know, like, what's the probability I see, out of all the, mortgages I have, what's the probability that like 5 of them foreclose or 10 of them, right? I might be interested in those for future, for making decisions about the future. So if I go here, oops, nope, I'm going to do this because I forgot 0. All right, what I can do is use that binomial distribution equation. I'm going to use these as different numbers of successes. So select this, then comma, the number of trials, comma, probability of success. And I just want to find the probability that it's exactly equal to these numbers of successes, right? Now the problem is if I try to copy this over, it will keep updating these number of successes, but it will also update these 2 cell references, and I want to keep using the same number of trials and probability of success. I'm just trying to find the different probabilities of different numbers of successes. So what I'll do is I'll freeze these cells. Now when I copy this over, I should have a row that gives me the probability that out of 100 homes, 0 are foreclosed. Probably that 1 is foreclosed. The probability exactly 2 is foreclosed. All right? So I copy this across. Oops, keep going. Notice we said the expected value here is 4.7. So 4 and 5 should be the most likely outcomes. And if I look at these probabilities, sure enough, 4 and 5 have the highest likelihood of occurring. And then as I move in either direction away from that expected value of 4.7, the probabilities of seeing those numbers of successes should decline. Sure enough, these probabilities are getting smaller. These probabilities are getting smaller, right? But this is, kind of a nice, easy way to get a bunch of different probabilities really, really quickly, right? And actually, I could prove to you that the cumulative is working as well, because I could just do, if I add up the probability that x is equal to 8 all the way down to 0, this number should be the same as 0.95397, right? If that cumulative option in the binomial distribution equation is working correctly. Sure enough, that's what I get, okay? Any questions on any of that, or want to see one of those cells again? B5? Yeah. Yep. So that was just where I was selecting those cells where I had X, N, and P, right? And because I wanted exactly 8, I didn't use that cumulative option. I just put a 0 in there. Yep. You only use 0 if you want the probability of just that one number, exactly equal to that number. Yep. All right, let's check that there's no, okay. So we should be good there. Oh, we got a couple minutes. So here's kind of the slides that have that. I'll probably hold off because honestly, I could start talking about it now. I'm just gonna have to repeat myself on Friday when we start it. But Friday, we'll start with and kind of work through this Poisson distribution, work through a few examples related to it, and that if we have extra time on Friday, I'll start going over a few questions from those practice exams. So if you have looked at them before Friday and you have a specific question, bring it to class on Friday and I can answer it. Like I said, today, actually this afternoon, also, I'll be filming me just working through a few problems on the practice exam in my office, just so like ones that I think are kind of easy and maybe don't want to waste any time on Monday or on Friday on. But also if you're running into problems, you can then watch those videos and kind of go to that specific problem and figure it out. And I'll try to do them in like little bursts. So I'll probably do like questions 1 through 5, questions 6 through 10, things like that. Okay. All right. If there's no more questions from me, I'll let you guys get out of here and I'll see you on Friday.